In this section, I'm going to go over IPsec basics, and we'll configure an IPsec VPN using crypto maps. So IPsec isn't a protocol. It's a suite of protocols, or a group of protocols used together to secure communication. It runs at the network layer. It provides confidentiality, integrity, authentication, and anti-replay. And the only reason anti-replay is down here is just because when we think of IPsec or many other security things, we think of CIA. It's our confidentiality, integrity, and authentication. Confidentiality means the data can't be read by an unauthorized user. Integrity means the data wasn't modified in transit. And authentication ensures the peer is the correct one. So we authenticate our peer or verify the identity of our peer. Anti-replay means that captured traffic isn't replayed back. And it's able to ensure anti-replay by including a sequence number on each packet. The device keeps track of the sequence number and won't accept a sequence number it's already seen or processed. IPsec uses two different types of packet headers: authentication header, or AH, and encapsulating security payload, or ESP. AH is protocol number 51. It provides integrity and authentication and anti-replay. Encapsulating security payload, or ESP, is protocol number 50. It provides integrity, authentication, and confidentiality, and anti-replay. So in addition to what AH provides, ESP also provides confidentiality, which AH doesn't. For that reason, we use ESP in more applications. It doesn't mean AH isn't used. It just means that we have more applications that we need confidentiality for. So from this point on, I'll focus specifically on ESP. We can run in two modes: transport mode or tunnel mode. Transport mode protects the payload. The original IP address is left in plain text. The original IP address in transport mode is what's used to route the packet. In tunnel mode, it protects the entire packet. The packet is encrypted, then encapsulated. So in this case, the IP address on the outside of the IP packet is what's used to route the packet, not the original IP header. So I have taken this picture from ESP's RFC 4303, not my picture, their picture. And they're in the section describing transport mode, and tunnel mode is where I've taken this from. Anyway, the picture here is describing transport mode, and on this side we're describing tunnel mode. In both instances, we have the original packet on top, so we have our original IP header, our TCP, and our data. After applying ESP in tunnel mode, so we have our ESP tags, our header, our trailer, and our CV. We have our TCP and our data here, but you'll notice in transport mode, we have the original IP header on the outside of the whole packet, and that header is going to be used to route the packet. In tunnel mode, it's a little different, right? It takes the whole thing, the whole packet. We still have our whole packet here. And we put our ESP tags on. From here to here will be encrypted. A new IP header is added on when we work in tunnel mode, or when the mode is in tunnel mode, right? So this packet the outside IP portion here is what's used to route the packet now, instead of the original IP header, because that's already hidden on the inside. So that's transport mode and tunnel mode. Now we have to look at Internet Key Exchange, or IKE. IKE is used to create secure tunnels for the control and data plane for IPsec. You have two phases in IKE. Phase 1, also referred to as isakmp SA, or isakmp Security Association. It builds a secure tunnel for the IKE exchanges needed in Phase 2. For example, keys. We have to exchange our keys for our symmetrical algorithms. Phase 1 is going to build a secure tunnel to do that key exchange. And then Phase 2, also referred to as IPsec SA, builds a secure tunnel to protect the actual data. One additional optional thing that can happen in Phase 2, or that we can enable, is perfect forward secrecy, which means it's going to derive new session keys instead of using information from the original keying. So we did our original keying, and if for some reason those keys are compromised, if I have enabled PFS, then new keys get generated without using any information from our previous keying process. That means that, if they've been compromised, we get new key information, which means we're not further compromised. So it's a good thing to enable. It is optional because it requires additional Diffie-Hellman exchanges or processing. So it is optional. We have two versions of IKE, IKE v1 and IKE v2. If we have IKE version 1, has two modes at phase 1. It can run in maid mode or aggressive mode, and then at phase 2 it runs in quiet mode. Well, what does that mean? In main mode, it hides the identity of the IKE peers, and it uses 6 message exchanges. If I run IKE v1 in aggressive mode, the identity of the peers are exposed, but it only uses 3 message exchanges, so it takes less time to negotiate the peers. So you just have to decide, okay, well, do I want to hide the identity of IKE peers or not? And then in phase 2, it uses quiet mode. Quiet mode has 3 message exchanges. Message 1 contains the agreed upon information in phase 1 and what traffic's being protected. Message 2 is the response with the matching IPsec parameters, and message 3 contains 2 unidirectional security associations. So it's a number of messages that have to happen with IKE v1. So IKE v version 2 was created to make the process more efficient. It uses less messaging. In addition to being more efficient and using less messaging, it also supports more authentication and encryption methods, such as EAP and next generation encryption. Because their messaging is so different, it's completely different, IKE version 1 and IKE version 2 aren't compatible with each other. So now let's look at the components that have to come together for us to actually secure our communications using IPsec. So we said IPsec offers the services of confidentiality, integrity, and authentication. It offers confidentiality by using these encryption methods, DES, triple DES, AES, or SEAL. It offers integrity using MD5 or SHA, and authentication using pre-shared keys or certificates. DES, or Data Encryption Standard, is a 56-bit symmetrical data encryption algorithm. Triple DES is basically, it runs DES algorithm, but it runs it 3 times with different 56-bit keys. AES is a symmetric encryption algorithm, and it supports different key links. So specifically, we're saying we don't want to use DES or triple DES really anymore. They're not secure enough. So we want to make sure that we're using AES, and we're choosing, as long as our devices can handle it or whatnot, that we're choosing a key length that's long enough, or the longest key length maybe that we can, that's reasonable for our infrastructure. Between MD5 and SHA, MD5 is considered something we don't want to use. We want to use SHA. MD5 is, I don't know if you'd say less secure, I guess that's how we don't recommend it any longer, so we use SHA or SHA. Diffie-Hellman is used for our secure key exchange between the peers. Specifically, it allows our peers to share a secret key that's going to be used with our encryption algorithms. Group number refers to the length. So when we talk about a Diffie-Hellman group or a DH group, it's referring to the length of the key. The higher the group number, the longer the key. So although we have group numbers under 14, we suggest that we use group numbers 14 or greater. Specifically, DH group 1 is 768 bits, group 2 is 1024, group 5 is 1536, group 14 is 2048 bits, and so on. So specifically, we're saying, you know what? Let's now stay away from groups 1, 2, and 5, and at least, at the very minimum, use DH group 14. And if you can use higher, great. And again, we have our anti-replay functionality, which just uses our sequence numbers to ensure packets haven't been captured and sent back. And I discussed it earlier. Basically there's a number attached to each packet. And as the devices process the packets, it keeps track of that sequence number. And if it sees that sequence number again, it knows there's a problem. So that's it for the basics. The basics are our protocols, our confidentiality, integrity, and authentication protocols we're using. Protocol used to enable devices to share a secured key, to generate and share a secured key, our anti-replay functionality, and now we got to go ahead and let's configure our IPsec VPN using a crypto map and kind of verify what it looks like. Let's go through the commands first. I'll just briefly go through them because I'm going to go through them obviously when we do this. So the first thing we want to do is create our isakmp policy with our crypto isakmp policy and then our priority number there. We enable the encryption under that, the authentication, the hashing, the Diffie-Hellman group, and lifetime is optional. If we want to specify lifetime, we can. Then we have to create our pre-shared key if we're using pre-shared keys, and we are going to. So we configure that using the crypto isakmp key, whatever key or password. The key is the same as the password. The keyword address, and then our peer address. So not our own address, it's who we're peering with on the tunnel. We'll create our IPsec policy, which is our phase 2, also referred to as our transform set, using the crypto IPsec transform set, the name of the transform set, and then our list of transforms. After we've done that, we've got to create an access list for the protected traffic, meaning the access list identifies what traffic is going to be protected. It also identifies what traffic is going to bring the VPN tunnel up, or the VPN up. Right? So when that traffic starts to come through that first router, that first endpoint of the tunnel, the ACL is what identifies the tunnel needs to be brought up. So that's what initiates the tunnel. It's the traffic that needs to be protected, and that protected traffic is what initiates the build of the VPN. And the ACL has to be mirrors of each other on each device. And this, you could use a named or numbered ACL. I'm going to use a named ACL. We've got to configure our IPsec SA lifetimes. All right, so the first thing we've got to do is create our isakmp policy with the command crypto isakmp policy and then a number. You can pick the priority number here. I've already just put one in. Then we have to specify our encryption within that policy, our authentication, our hashing, our Diffie-Hellman group. Our lifetime is optional. The default is 86,400 seconds. So we can change it, but if we don't, that's what it's going to default to. In this case, we're going to create a pre-shared key because we're going to use pre-shared keys. So we'll do a crypto isakmp key, and then whatever our key is or our password is, the keyword address, and then the peer IP address, so the other end of the tunnel. And then create our IPsec policy, also our phase, that's our phase 2, referred to as our transform set, using the crypto IPsec transform set command. Create our access list for our protected traffic. So the access list is actually what's going to initiate the build of the tunnel. I shouldn't say not the access list, not the access list itself. The traffic specified in the access list is what will initiate the build of the tunnel. When we see that traffic come in, the end device for the tunnel is like, hey, that's the traffic I'm supposed to protect. If our tunnel isn't built yet, let's build it. We'll specify that. You could use a named or a numbered access list. I'm going to use a named access list, so I use the IP access list extended name and permit our protocols. Configure the IPsec Security Association lifetime. This is IPsec. That's optional as well. And that's 3,600 seconds. Next, we've got to configure our crypto map and to link all this stuff together. So we use the crypto map keyword. And then we're going to match our address. In this case, we'll match our access list name. So match address and our access list name. We'll set our peer, which is the IP address of the remote device. And we'll set our transform set, which is just the name of the transform set that we configured in step 3. And then finally, we've got to apply our crypto map to the interface. This is the topology I'm going to use, a very simple topology. Let's just pretend, say that these are our 2 end devices. So let me see if I got my pen going here. Sort of. I'm a terrible drawer, as I think you guys know if you've watched any of these. We'll try to do this a little bit. We're going to create our VPN between R2 and R3. So we'll configure our IPsec VPN here. It's close. And basically what we're doing is we're pretending like router 2. It's got to go through router 2. We're going to pretend like router 2 is like our internet cloud. We could have a ton of routers out here. It could be a huge internet infrastructure. In this case, I've got 3 available. What we're going to do for my endpoints is I'm going to do addresses of 172. See if I can do this. 16. We'll just do 172.16.1. And we'll do a 24-bit subnet mask. So that'll be the network, and we'll make this end of our tunnel .1, and we'll make this end of our tunnel .2. So we'll look just a little more at the topology here. We've got 3 routers. The addressing here between R1 and R2 is 192.168.1.0 is the network. 1.1 is the IP address on this Ethernet interface here. And 1.2 is the address on this Ethernet interface. And I just want to do so when you see it as we go through it. So then when we build our tunnel, or I'm sorry, when we build our IPsec VPN, we're going to use peers of R1's peer is going to be 192.168.2.2. It's this inside physical address or physical interface address for the end of the tunnel. R3's peer then is going to be 192.168.1.1. And just an FYI for you guys, it has no effect on our IPsec VPN or anything like that. It's just what I had available and the way I built it is that these hosts are actually routers not running routing. They're simply have routing disabled, and their addresses are 10.1.1.10 and 10.1.3.10. What that's going to allow me to do is use these hosts after we've configured everything to ping through and build and see our tunnel get initiated. So this is our topology that I'm going to work with, and I'll go ahead and we'll get that going. I'm going to get rid of some of this ink here. We'll leave the tunnel information up. But you don't need all this extra stuff. This is, after we've explained it, it's just kind of in the way. Come on, I can't believe I used 2 lines to do that, or not. There we go. Okay, let's go ahead and start configuring. So the first thing I want to do is configure R1, and then we'll configure R3. Just an FYI, the routing is already configured here. In fact, we should go through and verify that everything works before we get started. So I'll actually bring host 1 over, and we'll verify that host 1 can get to host 2 over here before we build our VPN. Alright, so I brought my window over for host 1, and as I said earlier, this has nothing at all to do with VPNs or anything. It's just what I had already kind of cabled up or wired up. I'm using a router without IP routing running as my host 1 and host 2. So they're just dumb devices used so I can send traffic, so that we can send traffic to verify that first we're going to look at we have connectivity, then we're going to build our tunnel, or we're going to build our VPN, our IPsec VPN, sorry, and then we're going to see that it comes up and that it encrypts traffic when we send it from host 1 to host 2 and vice versa. So anyway, let's start with making sure that we have connectivity from host 1 to host 2. And as I said, the IP address for host 2 is 10.1.3.10. So we'll ping 10.1.3.10. Let's go ahead and do a trace route, because this is interesting information. Let's tab complete that. I'm going to do a trace route to this host, to host 2. And what you're going to notice is the number of hops it goes through. It's going to go from R1 up to R2 up here, that you can't see right now, down to R3, and then into host 2. When we build our IPsec VPN, it's going to use that directly and go right from R1 over to R3 to host 2. But first, let's just verify that that's true. So the first thing I want to do is prove to you that, yes, right now we have no IPsec VPN running, and it's going to go from R1, our packet will go from R1 to R2 to R3 according to our trace route. So it hit its default gateway, then it hit that inside part facing R1, then it hit the R3 address and went to host 2. So we have connectivity, we're good. Let's go ahead and start configuring our IPsec VPN then. Alright, so the first thing we've got to do is create our isakmp policy. Crypto isakmp policy. And then you give it a priority number. I just hit a question mark there to give you an example. I'm going to use 1. And encryption. Go ahead and look at our encryption options. We have triple DES, AES, and DES, just like we said. But as we also said, DES only has 56-bit keys. Basically, triple DES runs DES 3 times with 3 different keys. So neither one of them are considered very secure. We don't want to use those anymore. We're going to go with AES. Move my cursor out of your way. And hit a question mark so you can see the options there. We're going to go with a 256-bit AES encryption. Hit enter. The next thing we've got to do is our authentication. We're going to use pre-shared keys. Oh. Hash will be SHA. I should have finished it for you. Oh, can't spell. Oh my goodness. SHA. Hit a question mark. No, don't hit a question mark yet. There we go. Space and question mark won't work. Get to hit the question mark next to it to finish so we can get our length. We're going to use SHA 256. And our Diffie-Hellman group for our key exchange is going to be 14. Remember, we don't want to use anything under 14. If you hit a question mark here under group, you get your options again. But we're going to use 14. So we did our encryption, we did our authentication, our hash, our group. We're going to leave the lifetime at the default, so we don't have to change that. We're going to exit back and create our pre-shared key. So crypto isakmp key. You should use a better key than what I'm about to use. Remember, this is just an example. I'm going to use VPN pass as my password or my key. And the address is the address of the peer or the other end of the tunnel. What I want to be is the other end of my tunnel. So that's going to be the 192.168.2.2. That's this Ethernet interface IP address right here on the inside. And we hit enter. Next, we want to create our IPsec policy or our transform set. So crypto IPsec transform set. I'm going to use tab complete there. Give it a name. I'm just going to use VPN set. And then we begin the configuration. Let's start with our encryption. I'm going to hit a question mark here. And we're going to use, again, we have our encryption possibilities here. We're going to use ESP AES. And I just hit enter and I shouldn't have. Sorry about that. ESP-AES and hit another question mark. And there what we're going to get is our bit options. We'll use 256-bit keys here. So ESP AES 256 space question mark. Now let's do our authentication. Did not like that question mark. You that are just not responding. $256. Alright, well, it doesn't seem to like it. So our next part, what we're going to use for our authentication is ESP SHA. Weird. It's hitting it, but it's almost like it's not scrolling. I didn't even notice that. Okay, well, ESP SHA-256 HMAC is what we're going to use. So ESP-SHA-256. It's just faster than my eyeballs or something. I don't know. ESP SHA-256-HMAC. And hit enter. Our transform set is set up. Here's where I could do the mode, either tunnel or transport. The default is tunnel, which is what I want to run, so I can just type exit to go back one. And now next we've got to create our interesting traffic, or our ACL, that defines our interesting traffic or defines our protected traffic, or stated another way, the traffic that is going to bring up our IPsec VPN or begin building that. So IP access dash list extended. And I bet you guys can guess at this point, I'm going to go with VPN ACL. I like to pick things when I'm doing examples that I will remember. Permit IP, the source. So the first thing we want is the source, and then the source wildcard, then the destination wildcard. So since we're on R1, the traffic that we're going to protect is the traffic going from the 10.1.1.0 network, which this sort of represents our internal LAN here. I'm going to click on this and whoops, goodness. I'm going to click on this and get my pen. We're going to protect the traffic on what we consider to be sort of our internal LAN. This is just an example, and obviously you would never directly connect. Okay, I shouldn't say never, never say never. Rarely would you just connect a PC right there, but this is just representing on each side of R1 and R3. These are representing our internal network, our inside LAN. So our interesting traffic, or our traffic that's going to be protected, is the traffic going from this inside LAN over to this inside LAN. And then vice versa, because remember they have to be mirrors of each other. Now I got to bring my terminal windows back. Alright, so we bring the terminal windows back. We want to permit. What do we want to permit? What's our source? 10.1.1.0. And our source wildcard then, because it's a 24-bit subnet mask, our source wildcard then is the opposite, or the inverse. So it's 0.0.0.255. Our destination for this traffic is when the traffic is going to 10.1.3.0. So 10.1.3.0. And again, the wildcard is 0.0.0.255. And go ahead and enter, and that's all I'm defining right now as our traffic. Next, we've got to configure, or we don't have to, we can next, I have in the optional section that I can configure the IPsec SA lifetime. We're going to leave that as it is at its default of 3600 seconds. And next, create our crypto map that's going to link our access list, our peer, and our transform set together, and then apply that crypto map to the interface. And then we'll go ahead and do the same thing on R3 and test to see that it all works. So crypto map, give it a name, VPN map. That's surprising. And our entry number, we're just going to use 1 IPsec.isakmp. Oh, my cursor. Enter. Don't worry about that. That's fine for right now. We're going to match address VPN ACL. It's the name of our access list that's specifying our interesting traffic. And hit enter. Then we've got to set our peer. So set peer. And our peer is 192.168.2.2. It's that physical interface IP address facing us. And set transform set. Transform. And set transform, and our transform I named VPN set. Hopefully I spelled everything correctly, because that could be something you got to troubleshoot later if everything doesn't match. And we'll exit back one. What did I call this? I called it VPN map. So then we go into the interface. We're going to apply it to this physical interface closest to or facing, would you say, I guess in reality, facing the internet, right? So we're going to go int, it's a gigabit 0/0 interface, crypto map, and VPN map, and our name is VPN maps. Now we've applied the crypto map to the interface. Now we've got to go over to R3 and go ahead and set up our VPN stuff. And so we go over to R3. Okay, and again, we start the process over again. We got to create our isakmp policy. So crypto isakmp policy 1. Encryption, the encryption is going to match, has to match. AES, we use 256, right? Authentication is pre-shared keys. Hash was SHA 256. Actually didn't write this stuff down, so I wish I had you guys could talk back to me and say if I messed something up. We'll find out though if we have a troubleshooting section. If I end up having to troubleshoot, then we'll know I typed something wrong or I forgot one of my settings. Our group number is 14. We left the lifetime the way it is, so we can exit back out and create our pre-shared key. Crypto isakmp key. VPN pass address. Our address again then is the peer on the other side, so that's the 192.168.1.1. Whoop, 1.1. I don't know why it flipped over to R1 on me just now. What I hit, there we go. This is what we finished. It just clicked over to the other window, not sure why. Crypto isakmp key VPN pass address. Now let's go ahead and create our transform set, our IPsec policy. Crypto IPsec transform set VPN set. Whoa. Oh, I forgot to ask, so it didn't tab complete it when I wanted to. Transform set VPN set. What do we use? ESP-AES 256. Oh, now I can't remember, so I'm actually going to have to try to remember what. Oh, that's right. It was 256. Okay. ESP-S SHA 256 HMAC, and hit enter. And again, we'll leave it in tunnel mode so we can exit back out and create our access list for our protected traffic. IP access list extended, VPN ACL, permit IP. The source this time is traffic going from this LAN over to this LAN. So the source this time is 10.1.3.0, the 0.0.0.255, with the destination being 10.1.1.0, wildcard 0.0.0.255. Hey, and just an FYI, in case you're wondering, this name does not have to be the same name I put in R1, as long as I properly specify this in my crypto map. But I like things to be the same. Then it's very clear to me what's used for what. So go ahead and hit enter. I'm going to exit back out, leave our IPsec SA lifetimes alone, and create our crypto map and then apply it. So crypto map, VPN map, 1 IPsec dash isakmp, hit enter. Gives me my message again, that's fine. Match address, VPN ACL, and set peer to 192.168.1.1. My peer again, it's the inside here. The inner, what we call this, maybe the internet facing address. Even though we're pretending we have an internet with our extra router. And set, we've got to put our transform set in there, so set transform. And we called that VPN set. I hope I spelled it all right. That's it, right? We did our interesting traffic, our peer, and our transform. And hit enter. I can't spell transform, so there we go. Let's get that S in there. Move the cursor out of the way again. All right, we're going to exit back. Now, we've got to apply that crypto map to our internet-facing interface. So that's our one interface. In this case, it's gig 0/1. So int g 0/1 crypto map VPN map and hit enter. And we'll just type N to get out of there. Okay, so the moment of truth. I've got to open up both my hosts now. And I'm going to start at host 1 and I'm going to try to ping host 2 and we're going to see if that brings up our VPN. Alright, so host 1, we're going to ping 10.1.3.10. So we're going to ping host 2, basically. And hit enter. And it took a moment, which should have been the bringing up of the VPN, hopefully. So let's go into R1 and see if our VPN came up. So we can go ahead and verify that by doing it. Let's first look at phase 1. So let's first look at isakmp. So let's do a show crypto, if I could ever spell it right, crypto isakmp SA. And this is what you want to see here, a state of QM idle and a status of active. Our destination is 2.2 and our source is 1.1, 2.2. Perfect. Now let's double check that our phase 2 tunnel went up. We kind of know it probably did because our pings went through and our phase 1 is up, but we're going to check it by doing a show crypto IPsec SA. And what you're looking for there is packets encrypted and decrypted. And we did. We had 4 packets encrypted, 4 packets decrypted. So we correctly configured our IPsec VPN. Now I'm going to go ahead and tear it down. Clear crypto. Let's see if I remember the command. Crypto SA. Nope. isakmp. Okay, I'm forgetting something here. No. There we go. There we go. Clear crypto SA. Let's do a debug. Crypto isakmp. I keep wanting to put SA at the end of it. There we go. We're going to debug just so we can see it happen. And I'm going to bring up host 2. We're going to go ahead and ping from host 2 this time. 10.1.3, from 10.1.1.10. So again, it took a second because I cleared all the associations. We could have waited, but I cleared all the associations so that it would have to build that VPN again. So we could debug and see the process that it goes through. So if you're troubleshooting, if for some reason it didn't work and you're troubleshooting, use the debug crypto isakmp command to see if phase 1 is coming up. It means is everything matching? Are they agreeing on the things that they need to agree on? And you can kind of look through this. It'll tell you if there's an error, if something doesn't match, or if something has failed. And we didn't have anything that failed or didn't match. So that means that we have correctly... I mean, we knew that we had the parameters correct on our VPN for R1 and R3 as far as the encryption match, the authentication match, things like that. But I just wanted to verify, 1, that you could see the debug command, and 2, that we had the right interesting traffic on the R3 side as well. So R1 brought up our VPN, and R3 did as well. And we'll just verify that with our show crypto IPsec SA command to see our encrypted and decrypted packets. All these are the additional. So this I didn't clear this. So we still have our original 4 plus the 4 from R1 to R3 plus the 4 from R3 to R1 because I did not clear this. That's okay. So we encrypted, decrypted packages. We have successfully configured our IPsec VPN. Just a couple interesting commands that might be useful as you troubleshoot stuff. If you do a show crypto isakmp key. So if for some reason, say, They aren't actually agreeing on things. You could double check that your keys match on both sides. You can see with this command, you can see it in clear text. Now I'm going to hit the up arrow to bring the rest. I'm going to get rid of key. And I'm going to type peers and hit enter. And you can see who your peer is, right? So locally, because I'm sitting on R3 right now, you're 192.168.2.2. The peer, the isakmp peer, is the other side of 168. 1.1, which is this R1. So anyway, we are done. We successfully went through the basics of IPsec and configured an IPsec VPN using crypto maps.